This is George Gnachik. This is the first of what will be several videos that will outline the techniques, processes, and equipment used to measure the contour of the Earth's surface. I will be making the measurements on a frozen lake here in northern Minnesota on the Canadian border. The lake is called Rainy Lake. It's a large lake. It's 360 square miles. Half of the lake is north of here into Canada, and then there's another portion of the lake that goes out 40 miles to the east. The point of observation, or the base camp, will be here on the shore, the south shore of what is called Sand Bay, part of Rainy Lake. International Falls is on the west end of the lake. I live here about 7 miles outside of International Falls in the Lake District on Sand Bay. Sand Bay is about 5 miles across, and I'm establishing a point of observation up off the shore about 12 to 14 feet above the lake. So we'll be above the ice to minimize refraction effects. Refraction effects on ice tend to occur within the first 4 feet of height above the ice, but there's still refraction as you go higher, but it greatly is reduced as you get up off the ice, because the colder air is down near the ice, and you want to get above that layer so there aren't as much temperature gradients for the light to pass through, which would cause bending of the light. Now, point A is our reference point, and that is here. The coordinates is 48.614881 degrees north latitude by 93.308130 west longitude. There will be 2 measurement lines. One will be going northeasterly into Canada. True north, I will be showing some video following my presentation that you will see the actual physical topography. There is a high tension wire tower here on the Canadian shore, and true north is just a little bit to the left of it. So true north is in this direction here, and so our northerly measurement line will be a little bit to the east of that by about 23 degrees. And this length, I'll have a marker set up here on this island, on the shore of this island. This is 3.01 miles from the observation point to where there will be a marker on this island, and then we'll have 2 other markers out on the ice for making also measurements. Then the easterly leg will be going from the reference point on out to what is called Home Island. This is just about 7 miles out to this island, or 6 miles, 5.92 miles to the shore here. The coordinates are 48.643731 degrees north latitude by 93.185940 west longitude. And then we'll be setting up a marker here just off the shore of Franzen Island, and this is 2.76 miles from the observation point. The coordinates here are 48.627811 degrees north latitude by 93.251875 west longitude. Earlier today, I set up a marker pole halfway in between at the 1.36 mile mark from the reference point. The coordinates where this pole is set up is 48.62134 degrees north latitude by 93.27999 degrees west longitude. So that is the setup, and what we'll be doing is setting up targets on these poles. I'll be sinking poles and freezing them into the ice, which will be a very strong base. They won't move at all once they're frozen into the ice. And then we'll be setting up targets on the poles to sight with an auto level back at the reference spot. We'll be establishing a tangent to the earth at about 12 to 14 feet above the ice, a tangent to that position shooting outward in both directions, and then set up targets on these poles so that they align with the tangent line. And then once the targets are sighted and adjusted, we'll measure the distance from the center of the targets down to the surface of the water. What I'll be doing is drilling a hole at the base of the marker poles to let the water come up through the ice. The water will seek the proper level, the proper height with respect to the lake. The ice is floating on the water, so the ice has absolutely no effect as to the water level. You might have observed that if you take a glass of water, you put an ice cube or two in it and measure the water level and let the ice melt, the water level will not change, because ice always displaces its own weight in liquid water. So whether the water freezes and has ice floating on it, or the ice is totally melted, the water level will not change. So by drilling a hole in the ice and let the water level come up, we know that's the proper level. That will be the lake level in the summer when all the ice is melted, just as it is in the wintertime. That level remains constant. So that's what we'll be doing, is we just pop a hole in the ice, let the water come up, and we measure the distance from the surface of the water on up to the center of the target. I briefly outlined the philosophy, now I'll go into it in a little more detail. Suppose this is the ice. Currently the ice out on the lake is about 25 inches thick, 25 to 30 inches thick. And what I do is we bore a hole of about 20 inches deep, and we set our pole and freeze it in to the hole by pouring water in here and snow and make slush and let it freeze. Then this is a 10-foot sewer pipe. It's 4 inches in diameter, and to this I strap a 2x4. It's 20 foot long, and we take some hose clamps and clamp it to the pole, and then we mount our target on the pole. We can adjust the height of the target above the ice by loosening the cable clamps and moving the 2x4 up and down. This way I can get up to 20 feet of height above the ice, or as low as I need to be. But for all the targets, we're looking at being at least 14 feet, no lower than 14 feet above the ice. Then, back at the observation point, point A, is we sight with an auto level and get a tangent. And sight a tangent out away from the reference point. And we move the target up and down so the center of the target is in line with the tangent line. Once we have that, Then, on the day of making measurements, once all the targets are lined up with a tangent, we bore a hole through the ice and let the water level come up. Say we have our water underneath the ice, and it comes up. It'll come up within a couple inches of the surface of the ice. Then we measure the drop distance, or the distance from the center of the target to the surface of the water, and record that height. Now, also, when making these measurements along the optical corridor that we're sighting, every half mile we'll be making temperature measurements, barometric pressure, relative humidity. The temperature measurements, I have a thermistor stick, I'll show you in a moment, that gives us the ability to measure the temperature, vertical temperature profile of the optical corridor that we're sighting through. Now, once this is all recorded, then we can determine whether or not the Earth's surface is curved or is flat. Because if we have, say, several of these targets, and we've lined them up, see, this is a target here, this is a target here, and we've lined them up with a tangent. If the Earth is flat, then all these distances to the surface of the water will be the same. If the Earth is curved, then the targets, if we're back here and we shoot our tangent line, by the time we get out several miles, this target is, if it were at the same height as this target, would be below. But what we do first, before we make any measurements, is we align the center of this target to be in the center. The center of the target to be lined up with the tangent line. By doing so, then once we make our measurements, we will be able to know at what rate the Earth's surface is curving below, away from a tangent line. And the theoretical is that these drop distance from tangents should be about 8 inches per mile squared out. Away from, say, we have our reference point here. This is where we're sighting back here. Then our distances out, say in D in miles, then these distances here, drop distances from tangent, should follow this if the Earth is spherical. That as we go out, if we go out the first mile, this drop distance should be 8 inches below the reference. Say if this is 14 feet, this should be 14 feet 8 inches. And if we go out 2 miles, then this should be 14 feet plus 32 inches. Because 8 times 2 miles squared, 4 times 8 is 32. So this drop distance then will be 14 feet plus 32 inches and so forth. But if the Earth is flat, these distances should not change at all. So that's one way we can determine whether or not the Earth is curved or flat. Another thing that I'll be doing, this gives us a quantitative measurement. We can do a qualitative measurement also by strapping a second target to the pole. And this target on each pole will be at the same height above the water. That is, say we strap a target here at some height H. We do the same thing here with this target is going to be at a height H and so forth. Then when we sight this target should not be in line if the Earth is curved. If we have these second targets, this is a height H, this target is a height H. If the Earth is flat, again, those targets should all be sighted up in line. Their centers should be in line if the Earth is flat, if we sight the first target. But if the Earth is curved and we sight these targets, we sight this first target, if the Earth is curved, then this ought to be below the line of sight to the first target, and so forth. As we go further and further out, these should drop lower and lower. So that's a second test that we can use. Now, the motivation for using a frozen lake is several-fold. One, you don't have any swells in the wintertime, no waves to contend with. The water is still and quiet underneath the ice. And so there's no roughness to deal with. We pop a hole through the ice to get the water to come up, and then this water will be quiet, very quiet on the surface, and we don't have to worry about relative roughness and thickness of the ice by doing this procedure. The other thing is, up here in northern Minnesota in the wintertime, the air is crisp and clear. There's no moisture in here, very, very little moisture. The air is so dry up here in the wintertime, it's drier than the driest desert. Because when the temperature starts dropping down below 15-20 degrees Celsius, the moisture precipitates out of the air. You can actually see it during the day. On cloudless days with the sun out, you can have it snowing. There won't be any clouds in the sky, but moisture will just freeze and precipitate out of the air, and you'll have it snowing, and it's actually can be very pretty. You see the sunlight reflecting on these ice crystals as they precipitate out of the air. So the air is very clear and pristine. You can see outwards to 20 miles without any haze or any sort of atmospheric blockage whatsoever. The images are always crisp and clear. And what we do also is wait maybe for a breezy day, where ideally we want about a 10-mile-an-hour breeze so that there's air mixing. You don't want to be doing this on a calm, still day, because on a calm, still day, the air will layer. You'll get cold air near the surface, and it gets warmer as you go up. But if you have some breeze, you get mixing of the air, so a uniform temperature as you go up with height. So that's another thing that we want to do. And we also don't want to be making measurements near sunset or later in the day, because once the sun starts getting low on the horizon, the temperature starts dropping, and you get a lot of temperature gradients and a lot of refraction. The best times to be doing this is about midday or first thing in the morning, right as the sun's rising. The air really doesn't start elevating in temperature until about an hour after sunrise. It's a lot slower warming up in the morning than it is cooling down near sunset. So that's another thing to keep in mind. Now, let's discuss a little bit about the equipment that I'll be using. Here I have my Topcon ATB3 auto level. Its sole purpose in life is to establish tangents to the earth. It does not measure angles. Well, you can measure horizontal angles crudely with it, but it does not measure vertical angles, nor does it measure distances. The way this thing works is it has some optics in here that's attached to what's called a compensator. And the compensator you can think of as being attached to a plumb bob, a weight, and when the compensator mechanism is released, this is free to rotate, and it will point, its plumb weight will point down towards the center of the earth, or the center of the mass of the earth. So you're always having this thing aligned to a vector that goes to the center of the earth, and attached to this is a set of crosshairs. You can see inside the eyepiece there's a set of crosshairs, and these crosshairs float with respect to the housing and the tripod. The compensator always keeps this horizontal crosshair level with a gravitational equal potential when you're looking through the eyepiece. Now, what happened, what you do is you set up the base. There's a bubble level in here, and what it looks like is you have a little circular ring and the bubble floats around in here, and you try to center that bubble in the ring. And once that happens, once you get the bubble within the ring, the compensator releases and the crosshairs float. Then the way you can tell if the compensator is released and is working properly, you can take and you can lift this thing up a little bit. Say you aim this at something in the distance. Say there happens to be a pole out there, and there's you have a mark on the pole. Then if you pick up or tilt the auto level a little bit, the crosshairs will move off this thing. Say it'll move up or down, the crosshair will be here, and then when you release it and let it go down, the crosshairs will settle back to right at the same spot. But if you happen to move the auto level, tilt it up or down, and the crosshairs don't settle back to the same spot, then you know the compensator isn't released. So again, this is a very nice piece of equipment. Again, its sole purpose in life is to establish a tangent at where it's mounted. So you look out in the distance and you sight things within the crosshair. You know what's ever in the crosshair is on that tangent line here at the point of observation. You have a few controls. This is a fine control to adjust the auto level in the horizontal plane, right or left, to pan it right or left. There's a control here. This is the focus control. This happens to have a 28 power scope in it. And then sitting here you have an adjustment, and what this does, this is pretty neat, is as you adjust this control, these crosshairs will lighten or darken. You can make the vertical crosshair fade away, or the horizontal crosshair fade away, or them both fade away so there's nothing in the eyepiece, or you can adjust them so that they both have equal darkness and contrast within the eyepiece. So you have a little bit of control on your crosshairs also. So this will be the main piece of equipment that I will be using. I've calibrated this several times and determined its uncertainties. I can with confidence state that this particular auto level can get us within 5 arc seconds, or 5 seconds of an arc of a degree. 1 arc second equals 1 360th or 1/3600th of a degree. So there's 3,600 arc seconds in 1 degree. So this is pretty fine in adjustment in resolution and accuracy. I have calibrated my Topcon auto level several times and determined its uncertainty to be within 7 arc seconds. Let's look at what that means. 7 seconds of an arc, or 7 arc seconds of angular error. Let's see what that translates out to, say, out at a mile, what the uncertainty in measuring a height might be. If you recall that if we're looking out with a certain angular error, let's call it theta E, from a point, this is our observation, we're looking out here, and we have an uncertainty of theta E in our angular measure, which our theta E in this case is 7 arc seconds. Well, the relationship in a height measurement, if we have a radial distance out, say r, that's our distance that we're looking out, then the height uncertainty is that amount of arc that's swept out by this uncertainty in the angle. We'll call this S. Well, the relationship is that S equals R theta E. But remember that theta E must be in radians. This is radian measure, cannot be in degree measure in order for this relationship to hold. Well, 1 arc second is 1/3600th of a degree. And there are 180 degrees in pi radians. So 1 arc second works out to 4.848 microradians, or 10 to the minus 6 radians. So 7 seconds of an arc, we can use that. 7 seconds is 7 times this, or 33.94 times 10 to the minus 6 radians, or 33.94 microradians. So, at a distance, if we make r 1 mile, or 5,280 feet, then S is the distance out, 5,280 feet, times 7 seconds of an arc expressed in radians. So this is 33.94 times 10 to the minus 6 radians. This works out to 0.179 feet, or 2.15 inches. So, with my Topcon auto level, if I'm sighting out a mile, then the uncertainty that I have in a height measurement would be 2.15 inches. And it's a linear relationship. If we go out 2 miles, it'll be twice this. So if I go out 10 miles, let's say shoot 10 miles, then my expected uncertainty will be 10 times this, or 21.5 inches. Well, how does that relate to what we're trying to measure? If we are measuring curvature on a sphere at 10 miles, then the curvature on a sphere is 8 inches per mile squared. Well, if we're out at 10 miles, this will be 8 inches times 100, or 800 inches. Well, 21.5 inches uncertainty in 800 isn't very much. I mean, we're talking about close to 1/40th, which would be about a 2%. Now let's talk about temperature measurement. In order to determine the amount of refraction you have in your optical corridor when you're looking between your reference with the auto level and shooting a target, you need to know how much refraction there might be. Refraction is a strong function of temperature. Barometric pressure, relative humidity, they're like an order of magnitude less in terms of driving the refraction. So temperature is the main ingredient and parameter in determining refraction. So you need to know the temperature profile of your optical corridor. Surveyors, geodetic surveyors, usually just take 2 temperature measurements, one at the observation point and one at the target, average them, and then go to tables and determine the amount of refraction. However, I've been more detailed and nuanced in what I do. Is I built this thermistor array. There's 5 thermistors mounted on this pole, separated by 30 centimeters. And a thermistor is a solid state device that whose resistance is a strong function of temperature. So by measuring the resistance and knowing the relationship between resistance and temperature, you can get what the temperature is. These thermistors are type 44007 RCs NTC epoxies thermistor. NTC stands for negative temperature coefficient, meaning that as the temperature rises, the resistance of the thermistor decreases, and as the temperature decreases, the resistance of the thermistor increases. This type of thermistor has a nominal resistance of 5 k ohms at 25 degrees centigrade. There's very little thermal mass in these thermistors, which means that they're very fast in responding to temperature changes. If I were to take this thermistor where it's sitting in ambient air, throw it, dip it into some ice water, it would settle out within a couple tenths of a second. There's very little thermal mass. I've mounted the thermistors so that they're a couple inches away from the pole, so that any temperature of the pole does not affect the reading on the thermistor. Now, this pole can be extended up into the air by mounting it on another 10-foot pole or 20-foot pole and extend it up into the air to get the profile at a considerable distance above the ice. And I've typically, in the optical corridor, measured a temperature profile at 20 points above the ice, starting at 30 centimeters above the ice and going up 20 points every 30 centimeters. So that means up at 600 centimeters or 6 meters, which is close to 20 feet, a little over 20 feet. 20 temperature measurements. The relationship between temperature and resistance for this particular thermistor is 1 over the temperature is a constant A plus constant B times the natural log of the resistance of the thermistor plus C times the natural log of the resistance Q. A, B, and C are characteristic of a particular type of thermistor. You can look in the tables for this type of thermistor to get the A, B, and C. However, I've taken it a step further than this. I've actually determined the A, B, and C constants for each one of the 5 thermistors on my pole by calibrating each thermistor in a ice water bath that was temperature was established using laboratory grade precision thermometers. So I have these thermistors on this array very well characterized, and I can get the temperature to within, determine the temperature to within 1/100th of a degree Celsius. In this equation, the temperature T is Kelvin, where Kelvin is 273.15 plus degrees Celsius. So if you know your temperature, say you're at room temperature, which would be around 20 degrees Celsius, room temperature would be 293.15 Kelvin. So this temperature T is actually temperature in Kelvin. Now let's talk about the Topcon GTS 3C total station. This is a secondary piece of equipment that I'll be using. This is the Topcon total station. It's a GTS-3C. It has angular accuracy of 4 arc seconds. Now the way that this is a secondary piece of equipment that I'll be using. This is called a surveyor's total station. This is a Topcon GTS-3C. It has an accuracy of 4 arc seconds, or 4 seconds of an arc. It can measure vertical angles, horizontal angles to that precision, as well as distances. There's a laser, infrared laser inside here that's used for doing making the distance measurements. Now as you can see, as I rotate the vertical here, the angles readout is changing, and I can set it over to horizontal, and as I move the horizontal, it's reading out to within 4 arc seconds of on the horizontal angle. And the same thing with the vertical. And this has a 30x power scope in it. What is really nice about these total stations, if you want to read in the reverse direction, you don't rotate your total station around. You flip it over, and that's what there's a technique called reversion that surveyors use for determining leveling accuracy and errors. And so what you do is you just move yourself around, sight in the scope, and you can also rotate it around if you wish, but you can move the optics, flip it totally around like that. And there's various controls here for setting up the total station to make sure it's absolutely level. It's very critical. There's a little bubble level in here that gives you 30 seconds per division. And there's also a circular bubble level in here. And if you're not very close to having it set up to the center, it just won't read out. There's a compensator in this thing too, but it's not quite as accurate as the auto level. But the nice thing about the total station is it won't give you readings unless you're close to having this thing level. So It's pretty much foolproof. It's very hard to really fall up with this thing. So this is the total station. I'll be using it mainly just for measuring distances. And the way you measure distances is you also use, in conjunction with the total station, you have to have something to reflect the laser light back. And rather than using mirrors, you just can't shoot a total station at something and get a distance reading. You have to have some very good optics to reflect the laser light back, and that's the purpose of this. This is called a corner reflector. And the beauty about these corner reflectors is you don't have to precisely align it like a mirror. These are designed to reflect back light at in the reverse direction that it came incident into the optics. So if this is off this way and my laser light's coming this way, it doesn't reflect it out that way. It just shoots it right back at you in the same direction that came into the corner reflector. So these are much better than any mirror, like if you wanted to shoot laser light back to you, because again, the adjustment using these corner reflectors is not very critical in terms of alignment, because they are designed to shoot the light back exactly along the same vector that it came into the optics with. And then these are mounted on a pole that is precisely graduated, so you move up and down. And then these also have a calibration on here. On this side I have 0 millimeter offset. This side it's minus 30 millimeter offset, and you punch that into the computer in the total station so that you can get very accurate distance measurements. So these are the basic pieces of equipment that we'll be using, but the primary one is the auto level, because what we need is a precise tangent at the point of observation. We need to establish a very, very precise tangent from which to work, and that is the sole purpose of life for the auto level. The total station, it can do that, it can perform that, but not to the same kind of accuracy that you can get with an auto level. So what I'll be doing now from now on is posting weekly updates, just short updates as to where I am, how I'm setting the poles in, and making measurements. So that's the gist of it. That's the philosophy in making the measurements out on the ice. And until next time, we're signing off here. Let's now talk about the philosophy behind the target design. My targets are rectangular. They have a white background, and there are two triangles where the vertexes touch in the middle. And then there's some lines with a gap. These triangles are black so that there's a great deal of contrast between the triangles and the background. Now the reason the targets are designed this way is so that when viewing these several miles out, you cannot make a high degree of detail, the resolution, because you're so far away. And what we're trying to do is get these targets aligned so that the center of the targets are aligned with the horizontal crosshair of the auto level, so that we know that the target is on the tangent line. Well, by having two inverted triangles like this, is we can easily tell whether we're near the center or not. If the crosshair line, horizontal crosshairs up here in the fat part of the triangle, we know we have to move down and try to get it into the narrow spot between the two triangles. So it's much easier to adjust the triangles when looking through the auto level spotting scope to tell exactly where on the target you're at. Now, I have several targets and they're all different sizes. And the reason for that is perspective. If we look out at a distance, say here, objects of different size physically can have the same apparent size if they lie within a perspective triangle. For example, suppose we're out 1 mile and we have a certain angular dimension to that. We perceive this object out at 1 mile is having some angular size called theta. Well, an object out much further will have the same apparent angular size if it fits within this triangle. So say we're out here at 2 miles. If this target is twice the size of this target, its apparent size will be identical. So that's why I have different size targets, is we put the larger targets out at further away from the observation point and the smaller targets in, and they are ratioed such that when they are placed along the measurement line that they will all appear the same size in the spotting scope. Now, this phenomena of having the same apparent size with different dimension physical objects spaced at different distances from the observer is exactly what happens during a total solar eclipse. If we have, say, the Earth here, an observer on the Earth looking at the sun and the moon, the sun's out here and the moon's way back here, but it just so happens they happen to be of the proper size and space the proper distance from the Earth that their apparent sizes look the same. They're about 32 minutes in diameter, or a little more than a half a degree. Well, the moon is 1/400th the diameter of the sun, but the sun is 400 times further away from the Earth than the moon. So they both subtend the same angle. And so their apparent sizes look the same to us. That's why the moon's disk completely covers the sun's disk, is because the ratio of the distances are the same as the ratio of the diameters. If this is the diameter of the sun, this is the diameter of the moon, this is the radial distance of the moon out, this is the radial distance of the sun out, then it turns out that the diameter of the sun is to the diameter of the moon, as the radial distance out of the sun is to the radial distance out from the moon, and this is about 400. Now let's take a look at the actual physical targets that I built for this particular purpose. You can see the targets here that we used to put on the poles. These are the targets that I made last year, and I'll be using them again this year. The target on the left is 24 inches wide by 37 inches tall in height, and the targets are proportioned so that on the nearer poles we put the smaller targets, and on the further poles we put the larger targets, and the targets are proportioned such that when we view through the auto level that they all appear the same size, because the targets in the distance will appear smaller than their actual physical size, so we put the larger target out there so that For example, the larger target will be more than twice the distance away from the observation point than the smaller target here on the right-hand side.